Tech in 5.
Ever wondered how top tech companies evaluate coding skills in interviews? Mastering coding challenges is your key to securing that dream tech job. Imagine you're in a coding interview and presented with a unique challenge to develop an algorithm for nutritional balance in just 5 minutes. Are you ready? In this challenge, you're tasked with creating an algorithm to find the best protein-carb combination for a meal, aiming for a specific calorie target. Identify a pair from a list of protein and a list of carb items that gets closest to the calorie goal without exceeding it. Let's break down today's coding task. We're creating a function for pairing proteins and carbs. We take in 2 lists as our parameters. The first list contains tuples of various protein-rich foods, alongside their calorie counts. The second list is similar, but for carbohydrate-rich foods. We're also given a target, the ideal calorie count for our meal. Our goal is to pair one protein with one carb, so that their combined calorie count matches our target as closely as possible, without exceeding it. The function will return the names of the protein and carb that make up our meal pairing. With these inputs, it's time to dive into the code and see how we can solve the problem. If brute force is the first solution that pops into your mind, you're not alone. It's often our initial approach to tackle problems that involve finding the best match or combination. Let's walk through how this works for the challenge. In a brute force design, we simply check every possible combination of proteins and carbs. Picture it like a detective, examining every clue. It's thorough but not always the most efficient. Let's dive into the code. We start by initializing a variable to store the closest combination and set it to none. We also need a variable to track the closest calorie count, starting off with infinity. We use 2 nested loops to iterate over every protein, pair it with each carb. If the combined total is closer to our target than any previous combination and doesn't go over, we update our closest combination and calorie count. After checking all possible pairs, we return the protein and carb that make up our best combination. This brute force approach ensures we don't miss any potential pairing. But keep in mind, the time complexity of this brute force solution is O of n times m, which is not quickest. Looking at this matrix, you might wonder, can we skip some of these searches to be more efficient? The answer is yes. By sorting the proteins and applying binary search for the carbs, we can reducing the complexity. First, we can sort the proteins, which has a complexity of O n log n. This is the standard time complexity for efficient sorting algorithms. For each of the carbs, we perform a binary search on the sorted list of proteins. Binary search has a complexity of O of log n for each execution. Combining these 2 steps, the total complexity becomes O of n log n plus m log n. Now let's revisit our matrix with a different perspective. What if we sort both proteins and carbs first, and then apply the 2 pointers method? Let me show you how it works. First, we place one pointer at the beginning of the proteins list, and another at the end of the carbs list. This setup initially pairs a low-calorie protein with a high-calorie carb. Now, we calculate the combined calories. If the value is less than the target, we record this combination. Then, we move the protein pointer one step to the right to try a higher calorie protein option while keeping the carb option as is. As you can see, we now can skip the rest of search for this protein. We continue to calculate the combined calories. If the value is also less than the target, we check if it's the closest we've got to the target so far. We repeat this process, moving the pointers, checking the sums. If this value is more than our target, it means we need to reduce the calorie count. So, we move the carb pointer one step towards a lower calorie option. Now we compare the value again. Throughout this process, we're scanning through our matrix from 2 pointers, narrowing down to the best possible combination, reducing the time complexity to O of n plus m. Our code of the pointers solution is quite straightforward. First, we sort both the proteins and carbs by their calorie content. We then initialize 2 pointers. P pointer starts at the beginning of the proteins list, and C pointer starts at the end of the carbs list. As we loop through the lists, we calculate the total calories of the protein-carb pair currently pointed at. If this sum is within our calorie target and is higher than any we've found so far, we update closest sum and result pair with these values. The magic happens in the pointer movements. If current sum exceeds our target, we move the C pointer left to try a lower calorie carb. If it's within the target, we move the P pointer right to try a higher calorie protein. This dance continues until we've scanned all viable pairs. The function efficiently navigates through the options to find the closest match to our calorie goal. Got a different solution? Feel free to share your ideas in the comments.
Stay tuned for more videos on Tech in 5.